So for the first one, I want to find a formula for f of t assuming linear growth. So to determine a function here, I want to say I want to find the slope. And so the slope is going to be the change in production over the change in time. And I know that because I know time is my independent variable here because that's inside my f of t there. So if I do change in production over change in time, well, maybe we want to let t be the number of years since 2000. Okay, and so the change in production is in 2014 it's 55.4, and in 2000 it's 60.6, and then we have 14 years past 2000 and 0 years past 2000. So we have 55.4 minus 60.6, and I want to divide that by 14. So I get negative 0.3714, so 371, okay? And it says to interpret, so let's keep going. So that's my slope. Now it's a negative slope, and do we expect that? Well, if I think about it, in 2000 we have 60.6, and in 2014 we have less. So we should expect that we have a negative slope there. So that makes sense. And so then our function, f of t, is going to be the slope, negative 0.371 times t, plus our initial value. In 2000, it was 60.6. And so that's my linear function. Now, what are the units of the 0.371? Well, production was measured in million metric tons, and time was measured in years. So the units of this are million metric tons per year. Okay, and so what that means is that for each year after 2000, wheat production, since it's negative, it's decreased. And again, this is an average rate of change, so we'll say by approximately 0.371 million metric tons per year. Okay, on part B, it says find a formula for g of t assuming exponential growth or decay. Interpret the parameters of your formula in terms of wheat production. Okay, and so what I can do here is I know that my initial value is 60.6, and then if I divide 55.4 divided by 60.6, I'll get my 14-year decay factor. So 55.4 divided by 60.6, and that tells me what percentage change I have over a 14-year period. Well, I want to know the percentage change over a 1-year period, so I can take that to the 1/14th power to get my 1-year growth rate, decay rate. So I get 0.9936. So it wants me to round to 3 decimals, so let's say 0.994. How's that? And so then I can say f of t, or so we'll call it g of t equals 60.6 times 0.994 to the t. And then using each of the formulas, what is the expected wheat production in the year 2020? So again, 2020 is 20 years after 2000. So we're looking for f of 20, and we're looking for g of 20. So if I take 20 and I plug it into my function f, I'll have negative 0.371 times 20 plus 60.6. And if I do that, I get 53.18. And again, the units for this are million metric tons. Okay, and for g of 20, I'm going to do 60.6 times 0.994 to the 20th. And when I do that, I get 53.195. Oh, so I was round to do 0.195, so that's 53.20 million metric tons. Okay, and then now it says find a formula for this exponential function. So I know that to get from 1 to 3 is a change in 2 units. So if I do 2.56 divided by 4, that's going to give me my 2-unit decay factor. So to get my 1-unit decay factor, I need to take this square root of that, or in other words, take that to the 1/2 power. And so I get 0.8. Okay. And so that's my value of b. And so I know that y is equal to a times 0.8 to the x. So this is my function here, but I don't know what a is, but I can use this value, this x and y value, and plug it in and find a. So I know that 4 is equal to a times 0.8 to the first. So I can divide by 0.8. And I get 5. So I get, so a is equal to 4 divided by 0.8, which is 5. And so my function then is y equals 5 times 0.8 to the x. Let's just test it and see if it works. So if I do 5 times 0.8 to the first, I get 4. And if I do 5 times 0.8 to the third, I get 2.56. So this function works. The nice thing about this one is I can go back and check my work to make sure it works, and it does. For the next one, I have 4 functions that they're all exponential. So the first one says which one has the largest value for a, and then the next one, which ones have the same value for a. So I think what we need to do is we need to think about what role does a play in the graph of this function. So if we have y equals ab to the t, this a is my initial value. Or ab to the x, anyway, whatever. So that's my initial value. In other words, that's the value of y when x is 0. In other words, that's the y-intercept. Okay, so if I look at the various y-intercepts here, I can see there's a y-intercept there, and then 2 there. And so it looks to me like function b has the largest y-intercept. So I would say b on that one. And then which 2 functions have the same y-intercept? So it looks to me like function a coming down like this. And if I trace this up, it looks like function c. So let's say a and c here. And then it says which function has the smallest value for b. And so I think what we need to do here is think about what is the role that b plays. So b is the 1-unit growth factor. And when b is negative, or not negative, but when b is less than 1, we have exponential decay. Okay, and so if I think about that, I know that for functions a and b, we have exponential decay. So for those two, I have little b values that are less than 1. And if I look at this function b here, what I can see is that it is really decreasing at a much faster rate than function a. And so what that means is that the little b value is very small. So which one has the smallest value for b? So it would be the one that's decaying at the fastest rate. And so that's function b there. And which function has the largest value for b? So that would be when the growth factor is the greatest. So what I'm going to look for is the function that is growing at the fastest rate. And so I can see here that if I look at functions c and d, they both have a positive, or they're both exponential growth. But if I look at which one is growing at a faster rate, I can see function c is growing at a faster rate than function d. And so the answer for D is C here, because function C is growing at a faster rate than function D.